Welcome to this session of Shadow the Scientist. MegaCam eyes wide open on the sky at the Canada-France-Hawai telescope. My name is Jamaica Marshall, and I am the Shadow the Scientist Programs Manager. It is a pleasure to bring all of you together after your school day to learn about some astronomy here with our science hosts, Dr. Viraja Katu and Alexis Acohido. Now, Shadow the Scientist is an initiative that's brought to you by a team at the University of California, Santa Cruz. Now, for this session, you should be able to also unmute yourself when you need to if you want to ask a question. You can also put questions in the chat at any time.
Thank you so much, Jamika, and welcome everyone to the session. I am Viraja Katu. I'm a resident astronomer here at the Canada-France-Hawai telescope. We have Jasmine Silva as our remote observer today. So she's doing all of the work tonight, and this is almost towards the end of the night. And Alexis is here for us to answer more questions that you guys might have. So welcome everyone again. I am Viraja Khatu. I work as a resident astronomer. So there are different kinds of jobs when it comes to an observatory. And as an astronomer, I am responsible for the observations that happen during the nighttime with the telescope. I'll talk a little bit more about my job and everything, but we will actually start looking at some of what CFHT does, how we get data, how we set up for the night, and take it from there. Okay. So let me try sharing my screen.
You should be able to share your screen.
Yes, I am.
Okay. Sorry, let me make sure. What is this about the
Okay, can you see that?
Yes, we sure can.
Okay. So this is Google Maps, just to orient you a little bit to where we are located. This is in the middle of Pacific Ocean. So if you can see my arrow there, these are the Hawaii Islands. You can see it's very well in the center of the Pacific Ocean. And if I keep zooming in on this, we are right over here on the Big Island. So this is the biggest of the Hawaiian Islands. If I keep zooming in more, our headquarters, so where we are sitting right now in the control room. This is a remote control room. This is not near the observatory. So it is in the town of Waimea, which is over here in the north. It's already 3,000 feet above the sea level, but this is where we operate during the nighttime. And the telescope is actually located, and I'll change this map to, let me see if I can. So this is a terrain map, and if you can see, the mountain is right over here. So that's Maunakea, which is the biggest mountain over here where we have all the observatories. And the top of the mountain where all the observatories are is approximately at 14,000 feet. So the actual telescope is located right on the top, but we are operating from here, closer to the sea level. So that's the difference in the terrain that we have. And then you can see there are other some of the other mountain peaks all over the island. So this is where we are. If we look at why this is a very special location, it is useful generally to look at what's the light pollution around in the Pacific or around Pacific Ocean. So there are all the red colors over there. Those are the more those are places which are more affected by the light pollution. And if you can see, the Hawaii Islands are right over here. And if I Oh, I can go to this one. This specifically shows the light pollution on the different islands. The big island is again over here. There's quite a lot of pollution over here because there are two major towns. But if we look close to the center over here where the mountain is, there is not a lot of pollution from the light. And being above the sea level, 14,000 feet, is itself very useful because you are far away that way from the ground level. You cut off a lot of the atmosphere, so there's not a lot of atmosphere. There's not a lot of disturbance in the air. Maunakea is a shield volcano. It's a passive volcano, but it's a shield volcano. And what I mean by a shield volcano is there is a very smooth airflow on top of Maunakea. With the smooth airflow, you don't have a lot of air churning up and down. And that is very essential for the observations because when you observe something, you want the least interference from the atmospheric turbulence. So a very laminar flow of air on top of Mauna Kea is very essential for doing world-class astronomy. And this is what we get on top of Mauna Kea. So this is the actual telescope on the mountain. So you can see it's a 3.6 meter telescope, and what I mean by that is the 3.6 meter is the diameter of the mirror, the primary mirror of the telescope. And we'll take a look at those specific equipment a little later. But that's the mirror. So the dome is basically housing the telescope. The black sections over here that you see, those are all the vents that we have. There are vents up here. This is basically the shutter that goes up and down. It can open and close when we have to open up to the skies for observing. So that's where the telescope is. But there are a lot of other telescopes. There are 11 observatories right now which are operational on top of Mauna Kea. So this is a view of all the different observatories which are on the mountain. And if you can spot, this is CFHT right over here. So it's kind of like at the end of all this, the long road that leads to this side of the observatories. So that is where we have CFHT. And this is how the telescope looks from the inside. So this is a wide angle view of the inside of the dome. You can see there's the shutter over here. If you can see my arrow, that's the shutter. And then this is the telescope. This is basically the housing of the telescope. And the primary mirror sits right inside this part. And then we have the secondary mirror right on the top. Right now, there is an instrument in the place of a secondary mirror, but I will show you the pictures of where we have the secondary mirror on the top. And then there is either an instrument over here or there are instruments down over here. So that is the inside look of the observatory. And before we move on to other stuff, if you have quick questions, we'll take your questions first, and then I can move on to the more science side of things. You can unmute yourself if you have a question and want to ask it, or you can put it in the chat. Sure. Adrit?
I was just confused about this. I was just confused. So, like, which kind of a telescope is this? Because there are multiple telescopes on Mauna Kea. Like, there are radio, infrared, ultraviolet, optical frequency telescopes. So I'm not too sure.
Yes, sure. So this is an optical infrared telescope. And this is basically designed to observe with optical and infrared instruments. We have, I'll get to, if you have more questions, I'll get to that, but there are 5 instruments that go along with the telescope. We have 2 cameras. One is an optical camera, which we call MegaCam, which is the instrument which is mounted right now on the telescope. We are doing observations with that. There's a near infrared camera, and that is also a very wide field camera. MegaCam is also another wide field camera. There are 2 spectropolarimeters, spectropolarimeters are instruments which collect spectra as well as polarimetric measurements. They're usually useful to measure magnetic fields around stars. So there are 2 spectropolarimeters, one in the optical, one in the near infrared. And then we have a spectroimager, which is mostly in the optical, but also a little bit in the infrared. So that actually collects both spectra and images of the night sky. So 5 instruments in total. This is an optical infrared telescope.
I'll also mention that is a good point, that there are other types of telescopes that do that observe different wavelengths of light. So Jasmine and I used to work at the James Clerk Maxwell Telescope, which does submillimeter observing. We also have radio telescopes, as well as some of the telescopes that are more primed to do like ultraviolet, that end of the spectrum as well. And we have a bunch of questions in the chat. This is
So
awesome.
do you control the telescope remotely? Yes, we do control the telescope remotely. But the thing to realize is there are lots of things to do on the telescope in terms of managing the telescope, balancing it, exchanging instruments. So we have one instrument at a time. So there are instrument exchanges. There's a lot of maintenance around the telescope, around the observatory itself. So there's a lot of that we have staff who go up there on the summit and do a lot of work. But the observing happens remotely from here in Waimea.
As far as higher peaks to place the telescope, so the question in the chat is, weren't there higher peaks to place the telescope? Other places where there were even less light pollution, where there's enough flat land to place it properly. So as far as on the Big Island, so Hawaii Island where we're at, Maunakea is the tallest peak. And then like Viraja was mentioning, it's a nice shield volcano, so it's nice smooth airflow. So reasons why we might not put a telescope on, say, a higher peak, but with more jagged features, there would be less turbulence. So like Viraja was talking about, that like churning of air isn't as good for our observations.
There's a question about magnifying power. So I'm not familiar with this. Yeah, that's a good question. I'm not familiar with what exactly is the magnifying power of the telescope. But to measure in terms of, so magnifying power is useful when you want, it's a useful measure. It basically tells you how much magnified a specific object is. And yes, I'm not too familiar with the number itself, but we do have, but I can answer a little bit in terms of the quality of the images, just in general. So the quality of our images are usually at par, considering the weather conditions. So if the weather cooperates, then we do have really nice observations. And by good image quality, I mean we are able to measure the light, whatever we get from the objects itself. So that depends upon the resolution of the specific instruments, and that also depends upon the image quality. So how well are we able to distinguish, say, for example, noise from specific objects? So I think in general, we do pretty good in terms of what kind of science we can do.
I think it also leads into another question on the chat. What basis is the diameter of the mirror decided, and how is a large mirror made? So you can kind of think of it as, the larger the diameter of the mirror, the kind of like further back into space and time we can look. So We're just under 4 meters. The Gemini telescope and the Keck telescopes are much bigger. They're about 8 to 10 meters. So like almost, twice as big as the CFHT telescope. They can look further than we can.
Okay, so before we get to the other questions, I see there are some questions about the science, so I'll just chime in a little bit into mentioning what's the science part of CFHT. So this is one of the images taken with the CFHT telescope, specifically with MegaCam. And if you look in this image, this is basically every particle of light over here is a galaxy. There are some stars, so some of these round blue circles that you see, these are some of the foreground stars. So as you're imaging a certain part of the sky, there could be some stars which really shine really brightly. So some of these are foreground stars, but most of these are galaxies. So this is a part of the sky where we were imaging what's called the Stephan's Quintet. So Stephan's Quintet is these are 4 interacting galaxies. It's down over here, so you can see there's a lot of gas around the 4 galaxies here. So that's the Stephan's Quintet. The speciality of this image is it is taken in the low surface brightness mode. And what that means is when we are trying to image a part of the sky which is faint, we want to make sure that we are highlighting the different features, like some of the diffused gas that you can see in the region over here. We are able to capture that because we are imaging something in a low surface brightness mode. So there are a specific set of observations which are scheduled, and they're basically to observe something which is really faint. So there are certain number of exposures that we must do in order to combine them together and create an image which will allow us to see some of the fainter features. So that's kind of the story behind this one. So this is actually a part of the sky where we are observing a lot of different galaxies. We also do individual objects. So this is a picture of Andromeda Galaxy. It is an image taken again with MegaCam. So for individual galaxies, it's basically useful to study the stars, the kind of populations in the galaxies, how the dust is distributed, for example, in the disk of the galaxy that you see over there. So all the brown dark surface that blocks all the light, that is all of the dust. All the glow in the disk is all because of the stars. So individual galaxies is what we do. We also do clusters of stars. So this is an image of a globular cluster. Usually a globular cluster is useful to study the age of galaxies. They are farther away from they're a little further away from the center, but it's useful to study how the galaxy, what's the age of the galaxy, how the structure in the galaxy formed. And let's look at the next. I think there is one. This is an open cluster. So these are, again, a bunch of different stars. There's a really, really bright stars. So this is basically like a nursery, which is forming stars really young, really bright. And there's another image, but I'll show it a little later. I see a lot of questions coming in. So let's go back to the questions again.
Yes, okay, so really quickly, do people live near the telescope or closer to maintain it? So no one really lives around the telescope facilities. We do have day crew. Most of them live in Hilo, and so they'll go up about 4 days a week and they'll do maintenance on the telescope. I think that also fed into another question that asked about cleaning the mirror. So about every 2 weeks, we'll do kind of like a carbon dioxide dusting of the mirror. We don't want to wash it with water. We really don't want humidity on the mirror at all. So we use very cold carbon dioxide and we spray it on the mirror and it sublimates away, so it doesn't leave any humidity on the mirror, but it will grab onto dust and take it off. And then, so that's about every 2 weeks we'll do that. And then as far as like recoating our mirror, we'll do that every like 5 to 7 years. So that's like completely restripping the surface and putting a new one on.
So there's a question about what's the particular celestial object which you currently are focusing on for observing. So there are different targets that we observe during the night. There's only with one instrument, but the targets could be different. For some observations we actually observe the entire star fields. So this is basically just observing a patch of the sky, so everything that falls under that patch. Sometimes there are observations for individual galaxies. There are also moving objects that we observe. So these are objects in the solar system that are moving. So they could be comets, they could be asteroids. And I'll show you one example. This is an example of 2024 YR4. So this was these sets of images were taken with MegaCam. And it was so this was a near Earth asteroid, and it was useful. The CFHT observations were useful to determine that the probability of the asteroid hitting the Earth was almost zero. So these are other kinds of observations that we do. Right now, let us just check in with Jasmine. What is happening? She's controlling the telescope and the observations. So let's talk to her.
I was finishing up one of our PI programs for the night and finishing with Pristine, if you want to talk about that project.
Oh, okay. So Pristine, so this is one of our large programs that we do. It's one of the programs that actually does not have very strict requirements in terms of what kind of observations, the kind of observations that they need. So usually when conditions are not excellent, we can still observe this program. I don't know if you want to add something else in terms of like the observations.
No, sorry, I was like reading the questions.
Okay, that's all right. Okay, so moving on, I think there is
I'll talk really quickly and briefly about I'll try and add a bunch of questions together. So as far as however many people work at Canada-France-Hawai telescope, so we have a staff of about 40 people, and then about 6 to 10 people maybe will be going up during the day to do maintenance on the actual telescope facility itself. The rest of us work down here in Waimea. Because it is at high altitude, so I saw a question about what that can do to you physically. It's hard to work at altitude. Sometimes you get headaches. For me, like my joints hurt, you get kind of tired. So we have to make sure that we have really good safety measures in place to make sure that people are safe while they're working at the telescope. And that includes rules like you can't go past 14 hours working up at altitude. We do have a mid-level facility, so about halfway up the mountain is Halepohaku is what it's called, and there's like a cafeteria, there's some dorms, and so for the observers that still observe from the summit, they will stay there at that mid-level facility during their shift.
Okay, I'll cover a little bit about how the images are generated and put together. So MegaCam is a wide field camera. I can quickly show. I think there is a.
These
Okay.
are really excellent questions.
Yes.
I'm really, really impressed.
So this is the CCD mosaic of MegaCam. These are 40 CCDs together, and on the bottom you can see a 2-cent coin to just give you the sense of what's the scale of this figure. So these are 40 CCDs in total. So when we have MegaCam mounted on the telescope pointing at the sky, if you're basically looking at a patch of the sky 1 degree by 1 degree, so it's 1 square degree patch of the sky. It's very wide in terms of astronomical terms and how much we can do out of it. So that's the view. So when you're looking at images of the sky, you actually get you actually get your entire image broken down into 40 pieces because every CCD captures the image. Now the goal is to create one single image. So we basically have to stitch the images from these different CCDs together and form one single image. The process of doing that is non-trivial. There are lots of steps that go all the way from collecting an image with the telescope to actually generating the final image. We start with actually cleaning up the raw image. So if there are any artifacts, if there are any, and we can talk a little bit about that when we actually get to doing the calibrations. So if there are any artifacts, if there is any any non-uniformity because of the way the CCDs are manufactured. So any defects in the detectors itself, any defects in the individual pixels. There are some of the CCDs, some of the pixels in the CCDs which are not good. So these are bad pixels, and we have to mask them when we are trying to extract data from the detector image. So once we clean up the raw image, once we correct for the imperfections, at that point we can stitch the image together. And that is done. This is all done through a pipeline. So at CFHT, the astronomers who are responsible to schedule observations for a given night also do some initial data reduction. So that's pre-processing of the data before it is distributed to all the PIs, the principal investigators of that science. So the image is stitched together. And once that is done, we need to approximately calibrate the image. And by calibrate, I mean understand how much light is actually coming on from different pixels. And that is done by using a flux standard. So a standard star observation is basically looking at specific stars for which we actually have a very precise measurement of how much light comes from those stars at different wavelengths. That information is very critical when we have to calibrate it against an image where we are observing some patch of the sky, but we do not know how the light is how the light from these stars come in at different wavelengths. So a standard star observation is very useful when you have to calibrate the flux, that is the light coming in from images of objects which are not measured before. So that's one part of the calibrations. Other part of the calibrations are doing these flat fields. So we observe a patch of the sky which is absolutely plain with no clouds. And that is useful to actually correct for the illumination across the detector. So not all the detectors illuminate the light equally. And so having a flat field image, so having like a monochromatic patch, it is like having a monochromatic patch of the sky, and it tells you how the different CCDs are behaving in terms of capturing the light information. And flat fields are useful to correct those abnormalities in the detector. So these are basically the different steps that you have to go through in order to generate the final images. And I'll let Alexis take a few other questions while I pull up some of the raw images for you.
Yes. Okay. So I saw a question. It is not harmful to be at the telescope while it's observing it's less about anything coming off of the telescope, but we don't want to be, because it is moving, we don't want to be in the dome in an area where it could move and like hit us or, you know, get us stuck, anything like that. I do want to talk a little bit about the instruments that we have. So like Raja has been talking about MegaCam, we at CFHT can only have one instrument on the telescope at a time. So we'll have pre-planned runs for however many nights. So I think tomorrow we're switching to a different instrument, Spiru, which is actually in that picture right up here. But other telescopes like Gemini have like an instrument suite on the back of the telescope, and just by like flipping their mirror, they're able to switch the light path to different instruments. Sudden changes in weather can affect observations, and in fact is one of the things that Jasmine and I pay most attention to during the night. So if image quality, like Viraja was saying, gets worse, then we might switch to a program that can tolerate poorer image quality. And when we talk about image quality, we're talking kind of about like the twinkling of stars. So it's very romantic to see the stars twinkle with your eyes, but it doesn't make for good observations. I did also see a question about how we deal with where does it go?
So there's a question about, are the images obtained artificially colored using computers, or are these the true colors of the planets and stars? So that's a very good question. When you actually capture images of the sky, these are in different filters. So the main filters of MegaCam that we use with MegaCam are U, G. So U is in the ultraviolet, a little bit in the ultraviolet, not perfectly ultraviolet filter. It's a near ultraviolet filter. Then we have G, which is the green filter, R, red, I, infrared. We have Z, which is a little bit more into the infrared. We have other narrow filters, which we can use to observe specific lines. But the point is, when you are observing, you're observing with different filters, you're basically observing in different colors, because different filters basically optimize the instrument to observe at those specific wavelengths. When you put an image together, so those colors which are captured from those objects within different filters, those are the true colors. When you put the image together, at that point, you can artificially assign a color based on all the different filters that you're using. For example, if you collected the same observe the same patch of the sky in, say, U band, G band, and I band. So that is in the near UV, that's in the green filter, which is optical, and then I, which is the near infrared. You have to artificially assign some colors to the near infrared and the near ultraviolet filter. So you basically decide 3 colors for 3 filters. So usually for near infrared, it's red. For the green filter, you'll just use the green color. And for near ultraviolet, you'll use the blue color. So these are 3 different colors now. So when you're trying to put together the image with 3 different filters, the filters have captured the actual colors, and you assign those artificial colors so that you are able to distinguish the different true colors in the image. So this can be a little confusing. Let me know if that is not clear. I try to explain it more clearly, but that is basically what you do when you're trying to form a composite image, which is combining images in different filters to form one image.
There is a question kind of related to that. How are the ultraviolet gamma rays and
Have you
other
asked any questions?
other non-visible light portrayed in the results? I think the fast and quick answer is it isn't. So those filters are filtering out a lot of those other wavelengths of light. And then I think there was another question in there about like, you know, talking about like resolution, and if we have like lower resolution images, like what actually are we looking at? What kind of science are we doing? So the way that I kind of like to think about it, not so much with MegaCam because it's an imager, but with things like Spiru, with things like the submillimeter telescopes and stuff, when we're looking at wavelengths of light, each type of light, each type of what's the word I'm looking for? Like gas molecules and stuff like that, they all have their own spectral fingerprints. So their spectra will look different depending on what it is that we're looking at. And so like if we're looking at things in the atmosphere, depending on the spectra, we can determine what kind of gases are there present in the atmosphere, things like that. So I hope that answers that question.
So there was a question about, is there an algorithm used to develop the images taken? There is a pipeline designated for every single instrument. So there are 5 different instruments and there are 5 different pipelines. Now this is not the ideal case many a times, because if you have 5 different pipelines, which means you need to have really good knowledge of every single pipeline when you're dealing with images. So this is the work basically done by an instrument scientist when they handle the pipeline to process the data. So at CFHT, we basically do it this way. Not all observatories and telescopes work in the same way. As an example, there is another observatory on Maunakea called Gemini. The Gemini Observatory has a single pipeline to handle all of their instrument data. So there's basically one single pipeline which has different compartments, and depending upon which instrument the data is taken for, that compartment of the pipeline, so that part of the pipeline is used for the data processing. So CFHT is one of the oldest observatories on the mountain. It's more than 45 years old. And this is one of the reasons why we have different pipelines for data from different instruments.
Virja, I'm sorry, can we
Yes.
pause right there? We have multiple
Sure.
questions about what's a pipeline?
Okay, so when I mean by a pipeline, I mean a programming software. So thanks for that question. So what pipeline is basically it's a programming software. It's an astronomical software which can take in data. So by data, it can either be images or these could be spectra. So whatever data we get from the instrument, the raw data is taken in by the pipeline. We feed it to the pipeline. There are different steps that the software performs in terms of all the steps that I described earlier. So there's the first part of the pipeline will do the cleaning job. It will assign, it will take out all the bad pixel data. It's going to stitch together the different CCD images. Then the next part of the pipeline is going to do the approximate calibration. And finally, the output of the software program is going to be the final image. So that the pipeline is basically a piece of software that's going to work in stages to process the data and finally give the final image.
And there's a question about that. How long does that process take?
That's a wonderful question. So the time the process takes depends upon how many files you're processing and what kind of data you have. So sometimes the data are not that high of a resolution, which means that, and by resolution, I mean how much are we resolving the objects on the sky. So if you're processing low resolution images, then that will not take a lot of time. But if you are processing high resolution images, and if the number of files are too high, so you say, for example, there are 500 files, then that will take a long time. The processing for, I can give you, so I'm the instrument scientist for WIRCam. So I can give you an example with WIRCam. So WIRCam, again, is our wide field near infrared camera. So when I process the images of WIRCam, it can take me anywhere from, say, 5 hours to 36 hours to process the data. And that is not me all the time being on the laptop for 36 hours and doing the stuff. It's mainly that the pipeline runs by itself So it's when you start the pipeline, there is an automated process. So it keeps running, but it's just going to take that long to process all the files. So like 500 or 700 files takes a very long time for the processing.
And then when preparing the final images, are there any chances of error? What are they?
Yes, so there are. So in terms of chances of errors, every stage of the pipe, so every stage of the processing generates uncertainties associated with whatever calculations or interpolations are done at every stage. So for example, as an example, I can say, like when you are for example, calibrating the images. So the calibration of the images is done with standard star images, as I described earlier. So when you are calibrating the image, there's always a chance of there's always some uncertainty associated with how well is the flux measured from the star, which is used as a standard, and how well are you able to distinguish the points of light on your image itself. So depending upon, so let me show you actually the image at this stage. It will be easier to connect to what I'm saying. Okay, so this is an image. It's not a clear image, but just to tell you, when you're looking at a dot of light, it's basically different pixels. And say, for example, there are 10 pixels over here, but it's not, light is not perfectly distributed in 10 pixels, you know? The light can, the light, depending upon how fuzzy or how sharp your point source appears to be, you can have a very fuzzy distinction between how much light is falling in different pixels. So when you're trying to measure all the light collected by all the different pixels around, there is some uncertainty to how well you have extracted the light from individual pixels. And uncertainties are like that. So when you're trying to process the data, there are uncertainties at every stage that accumulate throughout the process, and you get a final uncertainty on the measurements that you do from the image. There was a question about okay, I kind of look. Okay, there was a question about how huge data volumes are handled. This is a very good question, because yes, there are huge volumes of data that come out. At CFHT, we are very fortunate to have the support of the communities in Canada, France, and University of Hawaii. So Canada and France are our major partners in CFHT, and they provide a lot of their resources when it comes to computing. So there are lots of computing resources. Some of the pipelines that we have for our instruments, for example, Spiro, the Spiro pipeline that we have, that is actually that was developed by people in France. Even the MegaCam pipeline was developed by the first instrument scientists who were on MegaCam, and and those were people from France. So there are lots of computing resources that we use from France. All of our data, which is archived, is like if it we archive all the data which is more than 1 year old, and all of the data sits in the Canadian Astronomy Data Center. So that's CADC, which is in Canada. So it's a very large computing facility in Canada that that provides basically like hundreds of supercomputers to work with the data, to store the data. And all of the CFHT data is housed at that center. So, so scientifically, when we have to work on projects, or when, say, for example, you want to access data taken with CFHT, say 15 years ago, you are still able to do that because all of our data is housed with that data center.
We have a quick question here. What
Sure.
is that black line kind of in the center of the image? You see
Oh,
that?
this
Yeah.
Mm-hmm.
So this is basically a little bit of flux leak from some of the stars. So some stars are bright. All the black spots that you see are all the bright spots in the image. This is basically an inverted image. So everything that you see black is basically where you're detecting flux. All the white is where there is all the background. So when you see this light leaking in, this usually happens when you're observing really bright stars. That the flux basically leaks off the pixels to the surrounding ones.
And connected to that, there's a question about how you develop those pipelines, what factors are taken into account when you develop the pipelines, and are they different for different instruments?
Yes, they are different for different instruments, totally different. The pipelines are developed in different languages. MegaCam has a pipeline which is developed in C, the C programming language. There is the CITEL pipeline. CITEL is our spectral imager, so it obtains spectra as well as images. That has a pipeline in Python. So Python is a very convenient programming language these days, but not all of our pipelines are in very comfortable programming languages. There are very old pipelines, so all the languages that have been used are pretty old. So we have some Fortran code, some C code, and so at this point, generally, we do not touch anything in the pipeline itself. These were developed a long time ago, and that those pipelines are really heavy in terms of how much computing power they need to process the kind of images that come out of our different instruments. So if that answered the question.
And then real quick,
Yes.
why is the image inverted in color?
That's a good point. So you can invert it the other way. It depends upon. So this is basically like an image that was generated by default. Usually images are shown in inverted color, but it doesn't mean that you cannot have white for the bright pixels and black for the background. Um, all of the imaging software, the data viewing softwares, they usually have different contrast and different schemes that you can use when you have to visualize an image. So this is just by default how the image shows up.
There's a bunch of questions about CFHT's role within the larger astronomical science community and like how we would compare with telescopes like TMT, telescopes like LSST, the Rubin Observatory. And so the quick and dirty answer to that question is that each telescope has unique instruments that can look at different things, is looking at different wavelengths. And so each telescope kind of has their niche. And then as far as ground-based versus space-based telescopes, we do have a lot of space telescopes. From like an economic standpoint, it's just easier to do ground-based observations. It's easier to do maintenance on a ground-based telescope. There are certain telescopes that are around just for surveying the sky. Things like Pan-STARRS here in Hawaii as well. So like a telescope like Pan-STARRS will survey the sky every night. We'll look for targets that the scientists might say, this looks interesting. We might want to follow this up with a telescope like CFHT, which happens a lot with our moving programs target when we're looking for asteroids. They might send other targets to other observatories as well to get more like detailed clarity on what it is that they're looking at.
So there's a question about, is there maintenance performed on the pipelines, and also why haven't they migrated to newer or better languages? So yes, in an ideal world, we would like to do that. We would really like to make use of Python for all of our pipelines. But that is not practically feasible because, as I said, the instruments are very old. So all of the structural setting of how the images are taken and how the older languages are actually used to do a lot of the processing. Um, it's mostly hardened in the pipeline. It works fine. But having said that, if there are at any point, if there are, say, any errors or anything that we notice is not happening well, we always make a point to change that. But we are required to do that in the structure in which the pipeline was originally developed, just because it's so old. Migrating to newer languages for such old pipelines, like those are 20 or 40 years old, it's extremely difficult. So that is part of the reason why it is not actively done. There was also a question about measuring the ages of populations using the different colors or the light that we measure from the stars. Yes, that is totally done as a science. So if you're looking at this globular cluster, globular clusters are usually in the halo. So when you look at the galaxy, the disk of the galaxy, let me go back. Oh, okay. So the disk of the galaxy over here, the disk has a lot of young stars, which means the stars will be more bluer, which means they are more recently formed and they're continuously forming. So really bright. As you move farther away from the disk, so mostly in the central blob, in the outer regions of the central blob, you will find globular clusters. So these are clusters of stars which are really, really old. And those are the stars that you mostly find in that in the central blob of the galaxy, or in the halo, which extends to larger parts of the galaxy. So when we see redder stars means more older populations. Bluer stars, as against that, so this is an open cluster, the Pleiades cluster. All of the hue that you see is all from the hydrogen gas, which is spread in this region. This is an actively star-forming region. All the young stars appear blue. They're young, so they shed a lot of light, and that is why they are so blue. The red stars are not actively glowing, so that is when you see all the redder colors. So that basically tells you that the halo of a galaxy, which is more in the outer parts and the central blob, is actually older than the disk of the galaxy. The disk of the galaxy hosts many of the young stars, so that is basically an actively changing region of the galaxy, which is much younger. So yes, you can tell the age by looking at the colors that we measure of these stars.
Switching gears just a little bit, I know this question was asked a couple times in chat, and it has to do with seismic activity in Hawaii. So yes, we do get a lot of earthquakes here, not only earthquakes, but right now one of our volcanoes is erupting. And so that stuff does affect us when we observe. There are different seismic detectors on the summit, and we share between observatories. So if one observatory detects seismic activity, the rest of us operators will, tell each other. One of the ways that we can look at whether or not it affects data is just by like visual inspection. If we're having our imager, right, and we have an earthquake occur and we're looking at the quick looks data coming in, and it looks like, they're not nice round stars, they're kind of like bean shaped or like kind of loopy. We can tell that way, and then in that instance we might just repeat the observation, things like that. Sometimes we do have earthquakes that are very small, and so they won't affect the data really at all, and so we can kind of just continue with observing. And then as far as the volcano, so not only do we have to worry about seismic activity, but we have to worry about the sulfuric gas that's let off as well. And so if there is a certain amount of sulfuric acid or sulfur dioxide in the air, and our humidity is relatively high, it can combine to create sulfuric acid, which would be very, very bad for our mirror coating. So certain things that we have to take into account as well. That was a really great question.
So what we see on the bottom right over here, these are the particle counts, the dust particle counts, and we can see right now it's pretty low.
Mhm.
So we need to have a low particle count, low dust particle count, in order to perform good observations. If you see any spikes over here in this plot, then it's not safe to open up the observatory, because we can have particles settling on the mirror of the telescope, and that would be very bad.
Yes.
Okay, so going back, I just want to show the. I have to open this.
So this most recent question that came in, so having public data versus releasing it after 12 months. So for the scientists that are giving us their proposals, they're usually using it to write papers, do PhD theses, stuff like that. And so we want to give them enough time to finish their papers, to finish their projects before releasing it to the public, just so that they can kind of get their papers and stuff done, as opposed to like citizen science things where that data is just made public immediately.
So just to give a bit more details about that. So there is a process in place when astronomers over the world have to request data for their own science. So this is a peer review process. There are basically telescope observing proposals. So there's a first proposal stage where people in Canada, France, University of Hawaii, or their collaborators can apply for telescope time. So they have to propose their science. They have to give a justification of their science case and what is the instrument that they want to use, what are the kind of data, and what is the significance of their science to broader astronomy. So that's the first proposal stage. There's a second stage where once the first stage is done, there's a process that down selects the proposals. Once those proposals are selected, they have a second stage where they have to enter their observations. So we have a software called Kalaho, and we use that in order to the astronomers who have proposed for telescope time actually use that to enter the kind of observations that they need. And when I say what kind of observations, I mean, say for example, they want to observe a galaxy. They have to tell in what instrument they want to use, what filter they want to use, how long the exposures should be, if they need like a minute of exposure or they need 2 hours of exposure. And that depends upon what's the kind of signal noise they're trying to get for their images. What is the signal, how much signal they want to get for their images, how much resolution they want to observe at. So they have to specify exposure times. They have to specify if there are any tight constraints in terms of times. So for example, sometimes there are follow-up programs for, say, LIGO, Virgo discoveries or of gravitational wave events. If that is the case, then these observations need to be timed. If there is a supernova that is going off in a certain galaxy, there's an exploding star, then there have to be so these observations are urgent, so they have to specify if there is any urgency to these observations. And there are different pools of observing of requesting telescope time, that they can do more urgent proposals or just regular proposals. So once they enter the observations, it all comes to us. So as an astronomer at CFHT, my job is to schedule observations to observe for a given night. So what I do during my daytime is according to the science priority. So we rank the programs. A rank programs are the highest rank that we have for our programs. There are B programs, C programs, and then there are snapshots, which are the lowest rank programs. Snapshots are basically programs that can survive any weather conditions. So according to what are the science priorities, astronomer, and when the targets are up in the sky, astronomers basically schedule observations to go for a certain night. And then as remote observers, Alexis and Jasmine here, their job is to be here in the control room 12 hours straight from 6 p.m. in the evening to 6 a.m. in the morning, and they execute all of those observations that they see loaded in the software. And when executing the observations, it's basically giving like it's basically like sending those observations to the telescope. And I'll let Alexis talk about it a little bit more with the TCS screen up here. So these are the remote observers basically send the observations to the telescope. And the telescope then points to specific parts of the sky depending upon where targets are. And that is how observations are taken. So I'll let Alexis talk about what she does in terms of pointing to the sky and what we are seeing on the screen right now, and how is that useful?
Yes, so like Viraja said, she is one of our Q coordinators and instrument scientists. So depending on the instrument that night, our Q coordinators will come up with certain plans to execute during the night. So, you know, which programs to observe when, as far as like what would be the most optimal. And then there are a couple plans depending on, you know, maybe if conditions worsen or we have really excellent conditions, things like that. So they send that to us, and that's like, if everything goes well planned, then I just have to execute it as is. However, we can't control the weather, things happen, we might have technical issues. And so depending on what those are, depending on what conditions are, it's up to our discretion, like me and Jasmine and the other ROs, to determine, you know, maybe we'll skip this program, maybe we'll observe a different program instead. Maybe we have to shift things around to optimize for slews and filter changes. So those are things that we're thinking about at night. As we're looking at this TCS screen, so
What's TCS?
oh, sorry, TCS stands for Telescope Control Software. So this is just a general overview of one of the screens that we see at night. And this gives a good snapshot of kind of all the parameters that we're looking at. So at the top, right where it says Waimea, so we're looking at universal time, we're looking at the universal date, and we're also looking at the local time. Underneath that, we have telescope and target. So that telescope coordinates, that's where the telescope is actually pointing, and then the target underneath that, those will be coordinates for where we want the telescope to point. So ideally they'll be the same as we're looking. We also have things like hour angle, local sidereal time, dome position, things like that. We'll have air mass, that auto guide. So usually the telescope will kind of guide by itself as we put in the programs. However, we do have special programs that we observe sometimes that'll do non-sidereal guiding. And so we'll have to take measures of, you know, how long the trails are in pixels, just to make sure that everything is tracking correctly.
Can you explain a little bit about what's sidereal and what's non-sidereal?
Oh boy, okay.
Just in simple terms, not technical.
Sidereal is tracking at the rate of the Earth's rotation, where so the stars move, it's about 15 arc seconds per second, and then non-sidereal is not.
Yes, there was a question about tracking the stars as they are moving across the sky, and that is what AutoGuide means. Is AutoGuide is basically guiding if I understand this correctly, it's basically guiding onto a certain star so that we are able to do our observation of the target as it is moving across the sky during the night. So when the telescope is in auto guide mode, it's basically going to move as the Earth is rotating, so that we are able to be on the star all the time and not lose it somewhere.
Yes. And then so just looking a little bit more at this TCS screen. So in the middle, there's a picture of, that's actually where the telescope is pointing, where the dome slit is pointing as well. And then on the right side, we have a lot of weather information. So how strong the winds are, what percent relative humidity is, things like direction, temperature. We also are looking at the bottom right, our servos for the telescope. So if the telescope is having kind of a difficult time settling because of strong winds, that's where we'll be able to see it. We'll see lots of larger spikes. In the middle at the bottom, that's just a graphical representation of what our weather conditions have looked like throughout the night. And then on the bottom left, those are auto guider corrections that we're looking at. So what the guider is doing to correct for conditions, as well as just kind of general centering on the star.
Yeah. Okay, so at this point, I'll switch a little bit to what's happening in the control room. So right now, Jasmine, it will start taking the flat fields shortly. And just a reminder again, the flat fields are basically observations of the plain patches of sky, so that we are able to get what illumination the illumination differences in the detector. Before that, she just finished doing the standard stars. So this was observing different stars that we use as calibrators to calibrate our images. And I'll quickly show how we actually observe these images as we take them. So this is actually the science viewer of MegaCam. So this is a quick look software that allows the ROs, the remote observers, to look at the data as they come in. So you can see the 40 CC. So this is the actual image which was taken just a few minutes back. So this is where we are looking at a patch of the sky, but we are basically observing one single star, which has known flux measurements at different wavelengths. So this is an image. You can clearly see the image of every single detector. There are 40 detectors over here. And what information is displayed on the left over here is just basic information about the patch of the sky you're looking at. These are calibration observations. So the queued service observing team is basically doing that. The filter used is GRI. So GRI is one of our broad filters. So we also have those narrow filters I was mentioning about earlier. We have a separate G filter, a green filter, a red filter, and an infrared, the near infrared filter. But GRI is our broad filter, which is a separate filter, which is mostly used for all of the observations of moving targets in the solar system. So this is an observation in the GRI filter. And do you want to talk a little bit about what are these red circles over here? I might not be able to explain.
So those red circles are looking at point sources. So it's just to help us identify where those point sources are. And so sometimes it kind of misses some of the bigger ones or some of the fainter ones, but it's just a general view, I think, of like for us to identify where these point sources are.
So if you scroll over the image, you can see the stars actually appear round, and that's important to note from the image. If there is some disturbance for whatever reason, if something happens and the stars do not seem round, they seem a little bit elongated, then it is not not a good image, and then we have to re-image that. There was a question that I saw just now.
The illumination differences between the CCDs, why are they arranged in this sort of irregular shape and not a perfect square or rectangle, and the gaps between the sensors?
That's okay. So these are really good questions. So there are illumination differences in the CCDs because it's just a manufacturing thing. Not every CCD is going to be manufactured perfectly and exactly the same as the other CCD. And we won't know it unless we put together the entire instrument and actually do observations with it and try to find out how each of the CCD is behaving. So just technically speaking, there are differences in the detectors. These detectors are also are powered by different amplifiers, so it also depends upon the very specific differences in the gain of every amplifier. And again, these are manufactured to be similar to each other, which means there should not be any major differences. But again, there could be differences, and those have to be taken into account. The way we can understand how it affects the images is only when we actually do observations of flat fields. So we actually observe a surface which is mostly equally illuminated all across, and then we can distinguish what's the difference in the illumination of one detector compared to the other. So that is why having flat field observations is so crucial when it comes to measuring the accurate flux from the stars that we observe with the CCDs. Why there's an irregular shape? I don't know specifically why there is an irregular shape for MegaCam.
Me neither.
Detectors are of all the different shapes. It can be circular, it can be rectangular, it can have a very weird shape to it. But in general, it does not really affect the kind of science that we can do, especially in the cases when you have really wide field detectors. So this is a very wide field detector, and you're observing at big patches of the sky. So it's you can still do science whether it's an irregular shape detector or not. So the shape of the detector really does not affect the kind of science that can be done with it.
Okay, so a couple quick questions. How do we know where the targets are? So there are other telescopes like Pan-STARRS I mentioned that do large surveys of the sky. And so when we're referring against finding charts sometimes for certain instruments to determine that we are looking at the correct point source. Is there a possibility that the telescope could picture the Milky Way galaxy itself? We can picture certain areas of the Milky Way galaxy, but because we sit inside the Milky Way galaxy, it's very hard for us. Like it's not possible for us to take like a face-on picture of the Milky Way. There's no selfie stick long enough that we could use to take a picture of the Milky Way galaxy.
It's basically like you're sitting inside your house, so you cannot image your house from outside. It's kind of that idea. There is a question about stitching the images together. And let me just go to that question.
How does one even identify a celestial body under some names? So again, it just depends on what we're referencing off of. So like there are long surveys with like lots and lots of catalogs of stars. And so usually that's what we're pulling from.
So when you look at the image, you're basically, so if you count the CCDs, so this is one CCD, the second, third, fourth, and if you count all of them, these are 40 rectangles. But if you look very closely, then every rectangle also has two different rectangles inside it. So there's a slight color difference that you can note, and that is because every CCD is powered by two amplifiers. So these are two different amplifiers, and when I was talking earlier about the difference in the gain in the two different amplifiers, it is that part that I was referring to, that every amplifier can have a different gain. So there are 40 CCDs, but there are 80 amplifiers, and you want to be very careful when you are processing an image with so much of structure, so much of mechanical structure, that you do it right, and that is part of the reason why the calibrations are taken. The images are combined together, so that's a so going a little bit into how the images are combined together. This is if you look at the CCD image, it's basically identifying every CCD image with numbered. So there is an x-axis number and then there's a y-axis number. So there are dimensions to the individual CCDs, but there are also dimensions to the entire image. So when the images are stitched together, the processing pipeline, the software that stitches the images together, very carefully considers of what's the ending pixel of one CCD and what's the starting pixel of the next CCD. So the gaps in between these CCDs are very, very carefully measured and known. And that is why we are able to, when we are putting the image together, we are able to subtract that region and put the image together into one single image. So that's how partly what the pipeline is doing basically when it's trying to stitch the CCD images together. So how do you handle issues like cosmic ray hits or noise in the CCD images? That's a great question. So just to step back a little bit, cosmic rays are basically the high energy particles that can randomly hit your detectors. So
and we see them all the time.
yes, they're very common. One very common and a very effective strategy is to take multiple exposures of the same patch of the sky and median combine them, or average combine does not work as well as median combine. So they're usually median combined, and when you median combine them, the pixels which are hit by cosmic rays, those usually get the values of those pixels usually get eliminated. So that is how cosmic ray effects are taken care of when you're processing the images. There could be other strategies to subtract the cosmic rays because cosmic rays are very high energy particles. So this is when the count values of those pixels will be very high. So there's also another way to set a maximum count value for your science image and use that as a cutoff to get rid of the cosmic rays, but that's not always an effective strategy.
There is one question that I thought was really important, a great question that I wanted to go back to, elaborating on the timelines of how we collect this data, what the proposal timeline looks like, and all the way to like when images are released. So for us, generally speaking, we'll release a call for proposals. So that's us asking, Canada, France, Hawaii to give us their proposals. And we do that twice a year. So we have 2 semesters, like we had 25A and now we have 2025B. And so we'll set out that call for proposals. They'll send us their proposals. This is maybe like a couple months in terms of like us evaluating and accepting proposals. And then the semester lasts for 6 months. So during that time, we'll be taking data for them. And then we send that data to them. They process it. They write their papers. Like we mentioned earlier, the data is proprietary for 12 months. And then after that, it's just kind of open to the public. So I hope that answers that question.
So that's usually when the proposal call comes out, it's a couple of months, it's the proposals are due just a month later. So and then once the proposals are submitted, there are at least a couple months before the results are announced. And then there's another month to plan the observations. So it's like a month of proposing time, 2 months of wait while the proposals are being reviewed. Then again, a month of time when you have to feed in the observations of the selected proposals. And then once that is done, we have another month for us to prepare the observing strategy during the entire semester of 6 months. So that's kind of how the timeline is. There is a question about how targets are identified and how they are recognized. So there are two things that can be done. One is there are known targets that you want to observe, and by known targets I mean we have a specific distance measurement and for those objects we know precisely the coordinates where we always precisely know the coordinates where we are pointing at. So when we want to look at a patch of the sky where our target is known, then we just point our telescope to that part of the sky. And these are celestial coordinates, so we know precisely where we are looking at, and we observe the object, we get the measurements and everything. There is another under types of observations are when we are looking at a patch of the sky. So we again precisely know where we are pointing the telescope, but there could be new objects in the field. So these are fields which are just observed as entire fields, but we want to recognize new targets in the field. So say, for example, you're looking at a field where you're looking at much fainter objects which have not been identified before. So we look at that patch of the sky, and the way we recognize and categorize in terms of distance is by measuring how much light is coming from that object. And at which wavelength. So say, for example, you're observing a specific filter and you're observing a star. You measure the light from the star. Once you measure the light from the star, you know approximately what distance it is. Because you do all the math all the way from how much light you're measuring, in what filter you're measuring the light. And that information is useful when you're trying to get a distance measurement to the star. And that is done by understanding how much light is traveling. We know the speed of the light, and we know the geometry that we use as the light is coming from the object to the Earth. So we can very precisely say what's the distance to that star. If there are new objects, we basically use the wavelength in order to calibrate the distances. In astronomical terms, the distances are measured in redshifts, and that basically gives you an understanding of how far away the object is. When we use imaging, we again, as I mentioned, we use observations in specific filters when we want to get the distance measurement to certain objects. When we are measuring with spectra, that's a slightly different process. For spectra, we basically have dispersed light. So we have a range of wavelengths that we are looking at. And what we use for a distance measurement is a very precise location of a given emission line in the spectrum. And I can try pulling up a spectrum actually. In the meantime, you can address maybe other questions.
Let's see. These are really, really excellent questions. I'm so thrilled.
Yes, the questions are really, really
Yeah, yeah.
very, very thoughtful, deep questions.
Let's see. So what about the CCDs?
There's one about the sources of errors that can appear in the images.
I'm not too familiar with like the data reduction side of things, so I'll wait for Viraja to answer that one. If one star is behind another star, will the telescope be able to differentiate? Not necessarily. If it's like right behind another star, the star in front might be too bright for us to see the star behind. And just depending on positioning, we might just not be able to see the star behind it. But that is a good question.
So the question about whether we can distinguish stars, as Alexis said, that not really, not in all the cases. And especially if the stars, if the stars appear overlapping in an image, it's also very difficult. So for example, if you want to do science of a specific object, and if the field is very crowded with a lot of different stars, you have to be very careful about extracting light information, because you do not want to extract the light information from the neighboring object. So you have to be careful when there are really bright stars in the image, because that can confuse with the objects that you're actually trying to measure. Okay, so this over here is an example of a spectrum. This is an AGN spectrum, an active galactic nucleus. My research area is AGN, so that is why I was tempted to pull up an AGN spectrum. So this is basically a spectrum of a supermassive black hole, but we're not. But the light from the supermassive black hole is basically light coming from all the regions surrounding the supermassive black hole. And this is how a typical spectrum of an AGN looks like. All the different spikes that you see over here are from different elements. And the H beta, so this is the H beta is basically the hydrogen beta line. O3 is oxygen 3, and by oxygen 3, it basically means that oxygen is doubly ionized. So O1 is just atomic oxygen, but when we have O2, it's a singly ionized oxygen. O3 is doubly ionized oxygen. So this is basically ionized oxygen in the region that's picking up. Now, if I'm observing an object which is totally unknown with spectroscopy, for example, I will basically look for very prominent emission lines in the spectrum. So oxygen 3, for example, is a very prominent emission line in this spectrum, in all AGN spectra. And with the oxygen 3 line, I will be able to precisely calibrate what is the distance to this object. And how do I do that? I basically measure all the flux which is inside the oxygen 3 line, and I compare what's the wavelength of that line compared to the laboratory measurement of oxygen 3. So when you are experimenting in the lab, if we doubly ionize oxygen, we will find it to be peaking at certain wavelength. So we compare what's the wavelength of this oxygen 3 line on the spectrum compared to the laboratory wavelength, and understanding how far away it is, how much offset it is from the laboratory measurement of the oxygen 3 line. We are able to translate that into how far away the object is. So this might be a little too much to grasp in terms of what I'm talking about, but if you have more questions, what do you mean by laboratory measurements? That is when we do experiments in the lab, and we are, so for example, when you ionize oxygen in the lab, there will be a specific wavelength when you will see an emission from the oxygen gas, and that wavelength is the laboratory measurement of the oxygen 3 line in the lab. So so you can read more about it, and if you have more questions, I will be happy to answer those in our further conversations. But this is how we are very or we can very precisely measure distances to objects which were not known before, and those are new objects. And if the wavelength, sorry,
If the wavelength is shifted in the spectrum, how do you even recognize the element anymore?
So that is because that's a great question. We recognize the elements. We can recognize it by the shape of the lines, and yes, not every time the shape of the lines are the same, but there are transitions which are very close. So, for example, you can see there is a very there is H beta over here, which is a broad line. So you can see it has wings of the line are very broad. And then there is oxygen 2 doublet. So when you are when you're comparing spectra side by side, you can actually make out the features in sequence, and you're able to recognize how much it has shifted. So it's partly looking at partly looking at the broader spectrum as against only individual lines. But when we are, so sometimes, for example, you can also have specific filters to parse out the lines instead of having one entire spectrum. For example, MegaCam has an H alpha filter. So instead of observing the entire spectrum and getting the H alpha line, you can actually have an H alpha filter in the camera and only collect all the light which is in H alpha. So that is one other way of getting information about emission features. It's the
And then what is the difference between those hydrogen lines? What do the numbers beside O3 signify?
So the difference in H beta, H gamma, and H delta is basically where the electron is dropping in the configuration of hydrogen. So H beta is the second strongest hydrogen transition that is seen. Then we have H delta. This is H delta, H gamma. So that is basically where the electron is dropping to in the inside the hydrogen atom. Oxygen 3, as I mentioned earlier, if I only write O1, for example, then O1 is ground state oxygen, which is atomic oxygen. So oxygen found in the atomic form. If I say O2, it is singly ionized oxygen, which means that one of the electrons in the oxygen in the oxygen atom has been kicked off. When I say doubly ionized oxygen, it means two of the electrons have been kicked off. So oxygen is no longer in an atomic form, it's in an ionized form. So this is basically ionized gas.
So Jasmine is gonna close up the telescope in a bit. So if we want to bring up on the stat serve.
Okay. So let us.
So she just got done taking flats in the morning, and so now we're starting our telescope shutdown procedure. So that includes slewing the telescope, making sure that it's pointed at zenith, making sure that the telescope slit is pointed north, closing our mirror covers, and closing the shutter as well, making sure all of our systems are off. And so we'll try and get that up on the screen so we can see it.
Okay. You can switch away. The webcam is down now, so maybe you can switch it.
Maybe look at the telescope.
Or actually, no. Yeah, let's do the mirror covers.
The covers first.
Yeah.
So this is the primary mirror of the telescope. So you can see, you can actually see the reflection of the top in the mirror. And the petals that you see all around the mirror, those are basically the mirror covers.
Yeah, so they open up kind of like a flower. So and then we'll see the opposite. They'll close in on themselves once the telescope is in position.
And if you want to go to, you can go to one of the vent cameras. Oh, yeah. And then we'll switch there and then we'll stop. Oh, we're almost done.
Okay, so right now we're on one of the cameras that are looking towards our vents. And so the vents were used tonight, so now the vent vanes are closing. The vents help with that nice smooth airflow, right? We're on an ice shield volcano. We want to take advantage of that nice airflow. So we try not to like close up the telescope so that the air is turbulent around the telescope.
So the telescope is parked north.
Oh, that's just due to when we turn on the lights, we don't want to affect the other observatories to the east and west of us. So that's kind of the reason why we point north.
Well, you can switch the mirror covers now that you're about to.
Okay.
And these mirror covers are controlled by our hydraulics. And you can see them closing up now. The reason why we would close up the mirror covers first before closing the shutter and opening up the mirror covers after the shutter is already open. We do that just in case there's anything on the shutter. Maybe there's some snow or ice from the night before. Maybe there's some humidity. We don't want any of that dropping onto the mirror itself. So we wait until the shutter is open before opening the mirror covers. And conversely, we wait for the mirror covers to close before closing the shutter as well.
The reason also the mirror covers close alternately is because the covers overlap each other. So that way we're not interfering in the closing and opening of the mirror covers. So there's one set of mirror covers that open first, and then the alternating set opens. And while closing, again we close in the same way. While there are other things happening, I'll just want to point out that's MegaCam. So that is actually the instrument which is inside the MegaCam. It looks like a disco ball kind of disco light kind of setup, but that is where the instrument is sitting inside this entire case, and that's at the top of the telescope.
Let's do the shutter. And then, so I'll talk about that question that just came in. How do we manage our sleep schedule if we work from 6 to 6? That is a great question. So generally speaking, for our schedule as remote observers, we have 5 nights on shift, and then we'll have about 10 to 15 days off of shift. So the way that I personally manage my sleep schedule is the day that I am set to observe. So like if I am so I start a night shift this coming Monday night. Monday during the day, I'll try and sleep as much as possible. I'll usually wake up around 3:30 p.m. And then come into the office. I get in a little bit early, about 4:35 p.m. And then I'm in here prepping for the night, reading the QC email, getting up the software that I need for the night, eating an early dinner. And then during the night, I'll observe. And then, we're closing up the telescope now, and I go home and I try and fall asleep immediately. So on shift, I'm doing nothing but working and sleeping. When I'm off shift, we'll have things that maybe I'll need to come into the office for, like meetings, things like that. I also help with outreach, so coming to talk to you guys today, go to classrooms and things like that. So it is just an issue of like time management. For me, it's a little bit easier. I live about 20 minutes away in a neighboring town, Maunakea. For Jasmine, it's a little bit more difficult. She works in Hilo, or she lives in Hilo, which is about an hour away. So while she's on night shift, she will stay at like a guest house that CFHT has for like visiting astronomers, for visiting interns, people that stay there temporarily. So during night shift, Jasmine will usually stay at that house. Yeah.
So while we are observing the shutter closing up,
Yes, lots of coffee.
I can talk a little bit about how it feels to do a cool job. I saw that question coming in. I think it feels wonderful. So just to talk a little bit about myself. So I always wanted to do astronomy as a kid, and I know astronomy is a fascination for most of the young kids. And you may not end up in astronomy, but for me, it turned out that astronomy was meant for me. So when I was, I was born and brought up in India. I am from Mumbai originally, but I have been living in Canada for 14 years, and I'm a Canadian now. But all of my education was happened in Mumbai. All of my schooling, my college, I started my bachelor's, and after my first year I left the college because we moved to Canada. So I did all of my education, but the rest of my education in Canada. I did an honors bachelor's. That's a 4 years bachelor's degree, different from what happens in India, which is a 3 years there. So a 4 year bachelor's degree, and in North America in general, how it happens is you can select a specialization you want to do in your bachelor's. So I specialized in astronomical sciences. So not all of my courses were in astronomy. There were a few astronomy courses. Most of them were physics and math. And as you may have figured from all of our discussion today, that physics and math is extremely essential if you want to do good astronomy. So physics and math were most of my courses. Another thing that's important is computer science. So if you want to be an astronomer, a lot of the things I was talking about, pipelines a lot, programming languages. So you want to make sure you are a good programmer. You're able to work with the software side of things. So computer science is another essential element that you need in your courses. Um, after my after my bachelor's, I did 2 years of master's degree in Canada. So that was again in astronomy, where I worked on a research project. I was taking more courses, and then after that, I did a 5 years of PhD. So that's doctoral studies, and that was again in astronomy with some amount of space exploration element to it. So basically, all of my graduate and postgraduate education was in astronomy. But as a kid, I was very interested I loved physics in general. So my favorite subjects in school were like physics, and I loved math. I did love a lot of history and a lot of geography, so no offense to that. But yeah, so those that's kind of like what my background is. When I moved when I moved here to CFHT as a resident astronomer, my job is kind of divided into different parts. One part of it is research, and I do research on, as I mentioned earlier, supermassive black holes. So I study some of the largest black holes, which are millions or billions of solar masses, which are at the centers of massive galaxies in the universe. So I study how gas moves in these around these black holes to understand how black holes form, how black holes grow, how they contribute to the galaxy environment in general. So that's most of what I do as a part of my research. I have a lot of collaborators in Canada because I have been doing all of my postgraduate education in Canada. So I work with a lot of people in Canada. And then over here, I support nighttime operations. So as we mentioned earlier, there is scheduling of observations that has to be done every night. So I work on scheduling observations for MegaCam and WearCam. I am also the instrument scientist for WorkCam. What that means is I have to take care of the data coming out of the instrument in general, just seeing that the instrument is functioning properly in terms of what data we are receiving. I have to take care of coordinating things with the astronomers who have proposed time on WorkCam. So staying in touch with them for their science priorities. I am responsible for processing the data that comes out of WorkCam. So when we are done with, say, recently we finished 4 nights of WorkCam. I have processed all the data for WorkCam, and now I have to distribute that data to the astronomers, to the principal investigators who actually proposed for it. So that is like the full start to end process of getting data with WorkCam, and I'm responsible to oversee that all of that happens well. The other side of my job is also to support any other things that are required around. So if there are if I could help with instrument exchanges going up on the mountain, then I love to do that. Not everyone is comfortable, and physically also there are different everybody is different, so not necessarily everyone is able to support that, but I like to help out with instrument exchanges whenever I can. I also do a lot of outreach, talking to you guys, as Alexis said. I lead the Shadow the Scientist program at CFHT. I also do a lot of outreach in the schools. We take the science, we relate it to the Hawaiian culture. We take it to the schools, talk to kids. CFHT participates a lot in the community activities, like food distribution in Waimea. We also do occasionally do a summer food distribution for the kids on the island. We also participate in the annual Christmas party that happens in Waimea. So there are small community things that CFHT also does, and I always enjoy to be a part of it.
I saw a question, what are some of the most interesting phenomena that we got to witness using CFHT? So I'll relate that to an earlier question. So I feel like that's kind of the coolest part of my job, is like playing my small part in helping to collect data to introduce like new science. So that's been really fun. As far as CFHT specifically, we, like, within the last 5 years, helped to identify like over 60 new moons of Saturn. So Saturn's moon count is just under like 130 moons now. Viraja showed it earlier, but there was an asteroid that, you know, we thought might hit Earth, and so like being able to do those observations and, you know, help to say with clarity, like, no, the asteroid's not going to hit. Some of the other science I've been a part of at other telescopes, so like at JCMT, we looked at the atmosphere of Venus, found phosphine in Venus's atmosphere, and we predict that, you know, that was created using biological processes. Jasmine and I have also been involved in the Event Horizon Telescope observations. So imaging black holes was something that had never been done before. You know, we helped with some of those observations. So stuff like that is really fun and interesting to me. As far as like my own personal journey, it's a little bit different from Viraja's. So I was born and raised in Hawaii on Oahu, which is a few islands north. And I moved out to the Big Island in 2015. I did not take any astronomy courses. I actually got my degree in mathematics. But as has been mentioned before, you need a lot of math to do astronomy, you need a lot of physics. And I wanted to work in a place that used my degree, but also was close enough to my family. All of my family is still on Oahu, so just a very short plane ride away. But yeah, that's a little bit about my journey.
So there's a question. There's a question about Bootus void. Do surveys with the MegaCam ever reveal faint dwarf galaxies hiding in it? So so I won't exactly answer that question, but I would mention that MegaCam does do a lot of large surveys. So what we have on MegaCam are large programs, and by large programs we mean there are huge patches of the sky that we observe, and we try to build a global map of the sky. And if I can bring up CFHT, just give me a second.
Also, that was correct in the comments. Thank you for catching that. As of March of this year is actually 274 moons of Saturn. So I misremembered that number. Thank you for catching that and correcting that.
So as part of the large programs, we actually build like a full we try to do like a all sky survey with MegaCam, and that is basically contributing to observe the entire sky, how much ever we can, and try to do any possible science out of it that could be related to dwarf galaxies or other objects. But the idea of doing these large survey kind of science is so that it is available to the entire astronomy community to do whatever science they pick to do. And that's the purpose of the large programs. It's not it is not science driven. It has some goals to it, but it's mostly so that everyone is able to make use of it. There was another question about if CFHT could be redesigned from scratch, what would be done differently? That's an interesting question. And again, I'll answer this question in a slightly different way. So CFHT, as I said, is it's an old facility, more than 45 years old. And it's a 3.6 meter diameter telescope. Now, a 3.6 meter diameter mirror is not a big mirror in terms of the sizes of the mirrors that are being built right now. There are already 10 meter telescopes. There are 12 meter telescopes. There are 30 meter telescopes in planning. There are giant Magellan telescopes. We have the extremely large telescopes, 20 meter telescopes to be built. So 3.6 meter is quite small in that sense. And at CFHT, we do envision the future of CFHT as being a larger facility. And by larger, I mean larger by the telescope size, the mirror size, that will support more science and more cutting edge science that is done over the world right now. So we do envision the future of CFHT as a 11 meter class telescope where we will be able to do spectroscopic observations. So we want to, by spectroscopy observations, it will be a dedicated spectroscopic facility. So we'll only do spectral observations, but of the size of 11 meter class telescope. So that's kind of what we are envisioning for the future. And it won't necessarily be like building CFHT from scratch. It will be more like a transformative facility, because we are looking into how we can keep our footprint. We can have the same footprint, but have a larger telescope inside the dome. So there will be a larger dome, but the actual footprint on the ground of CFHT will not change. Now, there are lots of considerations that go into building such a facility, and whether or not the current existing structure can sustain that kind of a facility, but that is something which is under the discussions. So that's kind of what we are looking at for the future. So there's a question, when doing such large surveys like the all sky surveys, is necessary to collaborate with other telescopes to view over a larger region of the space, or is the data from one telescope enough? So in the current age of astronomy, nothing is enough with a single telescope. You always want to look at more, and always want to get data with more and more telescopes. And the reason for that is multi-wavelength astronomy. So multi-wavelength astronomy is gaining ground really fast. It's growing as an area. So we want to make use of data which is at different wavelengths, and a single facility may not be able to, it does not provide all of the wavelengths. A radio telescope is not going to give you optical data. Optical near infrared telescope like CFHT is not going to give you ultraviolet data. You need space telescopes in order to get ultraviolet measurements, for example. So by multi-wavelength astronomy, I mean we are trying to study objects and fields and do science at different wavelengths. And in order to get data from different wavelengths, you need to observe with different facilities. For example, if I'm studying AGN are the supermassive black holes emit radiation all the way from radio to ultraviolet. So if I have to study supermassive black holes across the entire electromagnetic spectrum, I will not be able to do that with CFHT alone. I have to use CFHT. I would have to use space telescopes like the Swift Observatory or the Chandra telescope to look at the X-ray side of things. I would have to use radio telescopes like there's CHIME in Canada. There is the very large baseline array that observes in submillimeter and radio wavelengths. So I have to use data from all of these different observatories if I have to really understand what's happening inside the AGN. So that's multi-wavelength astronomy, when you're trying to piece together light information across the electromagnetic spectrum and try to understand what's happening inside objects.
And that's reflected in some of the programs that we see. Is sometimes in the program notes, they'll say, you know, we want to observe it. We want to observe this program on a specific date to coincide with our observations at another observatory, so that we're getting it at the same time.
So there's a question, what are some cool facts about CFHT that you can't find on Wikipedia or that we can tell our peers about? So I can tell you two things that come on top of my head. One is we are actually a small sized observatory. Now, that may be something that you might find on Wikipedia, I'm not sure. But when I say a small sized observatory, we have about 35 people in total. For me, as a community, it's very easy to bond with a company, an organization which only has 30 to 35 people, because I'm pretty sure I've met every single person in the company. And it's very easy to build those connections. It's an environment where we know each other very well. So I think the cool thing is that we are able to work as a family, as an ohana, as we call in Hawaii over here. So we are able to work as one single family, support each other whenever required. When I stepped into my role, there were lots of things that I wasn't knowing, I wasn't aware about. And so talking to people, talking to different staff which are on different teams helps you to get a sense of what's happening all around the company. So that's a cool thing, I think, which may not happen in very large organizations. The other cool thing is about the kind of science. Now that we have MegaCam right now, I'll just mention about the U filter of MegaCam. So this is very specific about science. But a cool thing about CFHT and with MegaCam that we can do only at CFHT is the quality of data that we get out of the U filter used on MegaCam is the best quality data in that filter that we can get from any telescope around the world. So in that way, CFHT can make very unique contributions, specifically in the near ultraviolet band when we're taking data with the MegaCam. So that's another cool thing. Do you want to add anything?
I'm trying to think, like, most of the things that are specific and unique to CFHT, we'll try and tell people about But yeah, like CFHT is involved in a lot of outreach programs that I'm very proud of. So the Maunakea Scholars Program was started here. So that's getting science proposals from high school students in Hawaii to actually like we'll observe their programs and give them data so they can kind of see what it's like as an astronomer at one of these telescopes. We also have a portable planetarium that I'll take to schools. So it's a big inflatable dome. It almost looks like an igloo. And we go inside and there's a projector that will project stars up onto the dome. We participate in programs like Journey Through the Universe. So that's going into classrooms talking about astronomy. Usually I'll try and do cultural lessons. So my current presentation is talking about the Hawaiian moon phases, things like that. So those are things that I really enjoy and like about working at CFHT.
So while Jasmine is packing up, she hadn't had a chance to talk to us a lot. So I would like to ask a question to Jasmine.
Yes.
What is the part of your job that you like the most and you like the least? I won't say you hate. You like the most, you like the least.
I feel like every night, you know, even if it's just a normal night, I feel like every night is a chance to have fun and party here all night, observing data, doing, you know, I have fun every day. I don't know. There's times I guess I don't like when I'm sleep deprived and you know I have to fight through those nights, but usually I still will make it fun. But I also like you, like when we get to go to the summit and get involved with work and getting to do outreach as well. So I like everything.
Yeah, I think by virtue of like us as remote observers, like working by ourselves is like kind of the best and worst parts of the job because like
Can
when things go wrong, like it's we're the first line of defense of like fixing problems and things like that. And so when things get difficult, you know, it's can be very nerve-wracking, right? Because it's like this is a multi-million-dollar facility. So just making sure we don't like break anything. But then like on the flip side of that, when we're able to problem solve, when we're able to, you know, save a little bit of time, be a little bit more efficient, that feels really good because we're helping you know, these scientists get their data, we're helping you know, with new discoveries sometimes, like so stuff like that is really, really cool.
Well,
So there are still a lot of questions percolating. So
yes.
if Jamaica, if you can send us those questions, I will make sure that all of the questions are answered and they reach out to all the students.
Thank you so much. Yes, I have the chat saved. I was just going to ask if I can do that. So perfect. I will definitely send you all those questions and share them back with Manisha so that the students can get your responses. These were absolutely fantastic, such deep thought-provoking questions. Thank you so much. Can definitely tell that you put a lot of effort into preparing for this session. So we appreciate that so much. And I see some hands up, but we do need to wrap up actually here. So go ahead, actually, if you can put your question in the chat, I'm recording the chat so that way I can send it to Viraja and Alexis and Jasmine, and they can respond to your questions. So you can just add them in the chat there for me. I know this is the end of your school day, so it's about almost 9:30 there, 9:40 there in the evening for you students. So thank you so much for being with us. I really, really look forward to your feedback. I'll be sharing a follow-up survey with you, Manisha, for the students. And I'll share those with Jasmine and Alexis and Viraja. And I'll take it back to the control room for the final words before we log off.
Well, we just want to say we really enjoyed having you guys. The questions were excellent. So I really want to give a round of applause for all the questions coming in. You were really thoughtful about asking all of the stuff. and also pinpointing where we might miss some of the stuff that we're talking about. So thank you so much for all the questions. Thank you, Manisha, for coordinating the event. It's really nice to see all of the students so eager to learn about astronomy. And thank you, Jamika, for supporting this, for coordinating the entire event, and for organizing that. So thank you so much, and back to you, Jamika.
All right. Thank you so much.
Before Javika ends the session, I wanted to say thank you from the entire Lodha Genius Program team, Ashoka University. That it was actually in the beginning, I was counting the number of questions the students were sending, and after a point in time, I totally lost the number of questions. And then with the kind of rigor and consistency, you both were answering each and every question with so much detail, and making the language so lucid that they understand the concepts behind it, was just amazing. And Jasmine, thanks to you as well. You have been working in the background, I know, but thank you so much for that. And Alexis, thanks to you as well. You have been so kind to read each and every question and respond to majority of our students. I know, students, that you will still have questions, but like we promised, we will give you an opportunity to ask the remaining questions which you're left with. You have school early morning tomorrow, so I'm sure you should also have dinner if you haven't had, and sleep properly. Over to you, Jamaica.
Wonderful. That's a perfect way to wrap up. Thank you all so much. Everyone, students, have a good evening and have a great school day tomorrow and the rest of the week. We'll hope to see you again in a future session. Virja, Jasmine, Alexis, mahalo nui loa. Have a great rest, and we'll see you in a future session. Mahalo. Aloha.
Thank you so much,
Thank
everyone.
Thank you so
Have a
much.
good night.
Bye-bye.
Good night.
Bye.